Today we are going to talk about effects of air and water in ammonia system. And tomorrow we will talk more about system performance, system efficiency, and then we will also talk about in case of ammonia leakage, what are the how the personal protective equipments are to be kept, and how you to do give an emergency response to systems, and then how to handle ammonia refrigerant and oil. So slowly, we are going to the more complex part of the ammonia as a refrigeration system. I hope this presentation so far has been useful to you. Please do ask questions if you have any doubts. We can always keep on talking about it. Uh, in fact, I think some more people are yet to join, right? Chandana sir?
Yes, sir. Still
Yes, so
there
we maybe we can discuss. Yes, some more people are yet to come. So maybe next 5-10 minutes we can discuss what we have done in last 3 days, and then go
that's
for
better.
the presentation of it. So
Yeah, yeah.
as has anybody has any doubts or what has been told, what has been shared in last 3 days for anybody has? See, ammonia is basically mostly it is a site-built refrigeration system. Other than chiller packages, most of the things are built on site. So they are made or they are designed as per the customer requirement. It's not normally you are buying a 5 TR, 10 TR, or 15 TR package and combining and putting it into the system. It is more of custom built, custom required design. So we try when a consultant or engineer try to design a system, we try to understand the requirement of this your customer. He try to analyze, understand his process, how he is going to run the plant, what his actual objective of the plant, and then how in future he wants to expand. Because ammonia systems are normally people who are running plants with ammonia system, they keep on expanding, increasing the plant capacities. Uh, so these systems are totally side built systems. Here you need very good knowledge of system engineering design, understand process of refrigeration system and the customer's process requirement, what he wants to achieve by that, whether he wants to use as a cold storage. Even if it is a small cold storage, it can be if it is very close to the city, it may be a daily loading unloading thing happening in that cold storage. But it is located far away from city, it may be loaded in one, like you have a potato cold storage in India. They are loaded during February, March, and April. They are totally packed, maybe 5,000 ton, 10,000 metric ton, or 20,000 metric ton is stored in 2 to 3 months time. Then it is hold on for that maybe 4 or 5 months, and after typically August, September, they start partially unloading or selling those potatoes. And by November end or December first week, these cold storages are empty. Then December, January, they go for a maintenance of a cold storage and again start loading in February. Whereas a cold storage, which is more of a service provider cold storage for items like butter or ice cream, they are close to the city, and they may be once in a week the material is loaded into cold storage, but every day there is outflow of the material. So these different applications needs a different kind of engineering design expertise, and that is what an ammonia engineer does. And when it goes to the plant erection commissioning, it has to be done as per the drawings provided by the design engineer. It has to be followed all the practices which are mentioned, how to lay a pipe, where should be the slope, where should be the joint, whether I should use a stop wall in straight wall or angle wall, how do I avoid loops. All these things are to be followed when you are installing and commissioning a refrigeration plant. And once the plant is commissioned and running, it is responsibility of the plant manager and the plant operator to run the plant efficiently and safely. As we all know, ammonia has a toxicity we need to make sure that ammonia is the ammonia content or content of ammonia in plant is safe, kept safe, and it's run properly. Also remember that this ammonia refrigeration system is one of the highest efficient refrigeration system. There is no other refrigerant you can give you the similar performance for any temperature range. It is a one refrigerant common for -40, -50 degrees centigrade to +10 degree, or even nowadays air conditioning, we are talking about +15 degree. So it's a one common refrigerant. If you see in when we talk about synthetic refrigerants, depending on temperature and requirement, we always use different types of refrigerant. For air conditioning, we are using R134A. For low temperatures, we are using R404A. If you want to go below -30, -40, you are maybe going for R22 or equivalent refrigerants like that. So these various refrigerants are used for different applications. And secondly, these refrigerants, synthetic refrigerants, are mostly the mixtures of refrigerant. It means they are a combination of different gases. So when such a refrigerant leaks, you don't know which kind of gas has leaked from the leakage, and you have to remove all the gas and charge the new one. It does not happen same with ammonia. Ammonia can be simply topped up. Puranikar sir has already explained on day one what are the other advantages of ammonia. When it comes to plant operation and maintenance, you are running plant at desired suction pressure, and desired or designed discharge pressure gives you the highest efficiency. Ammonia plants are in working condition for many years. There is no, actually, it's not like other refrigerants that these plants get invalid or need to replace with a new kind of refrigerant. I have seen ammonia plants I have seen so many plants in India for running in 40, 50 years. Even few years back when I was in Sri Lanka, I visited some of the your sea fishery board plant, which was installed almost 30, 35 years back with stall vertical screw compressors. So Sri Lanka also has got a lot of history of ammonia plants, and India, of course, is a rich one. It has got more than 100 years of ammonia being used as a refrigerant in India since 19. As per the data available with us, the first ammonia plant for ice plant was made in 1914. The first cold storage in India was built in around 1935, and it has been growing, and industrial use is coming up very well. Now we have a lot of food processing industries happening, whether it's a seafood, meat, or vegetables, chicken, poultry. They are all are doing extremely. They are all running, and more efficiencies coming up because of the ammonia. In many cases, we have observed that in some of the plants, electrical energy becomes the most dominant factor into the running and operation cost, or what we call as the OPEX of the plant. So here, ammonia gives you far better and superior results. So that has been, we are trying to share with you what our experiences are there in last 30, 35 years of industry. We are trying to share it for last 3 years, last 3 days. We'll be trying to do today and tomorrow also. Anil, you'd like to say something?
Yeah. Okay. This ammonia refrigeration plant is what we are discussing. Tomorrow again we will have a good amount of discussion, and it will be like ice on the cake, because we have gone through entire basic things and how to put it together, and what is the advantage of all those if we all follow what we have discussed in today and last 2 days. It will be a great experience for everyone and great knowledge sharing in order to have a proper ammonia refrigeration system. And I hope it will also help to remove the hesitation in everybody's mind that we should not go for ammonia, or ammonia is going to be banned, ammonia is bad. So that kind of propaganda we should not we will come to know that it is all false, and we should go for ammonia refrigeration system, because it has a most advantage like energy efficiency and the natural refrigerant as an ammonia. So, and this is going to be the future. So all these, whatever you have conducted is going, it's at a right time and at a right place, as you all are trainers and you are going to be the key persons in promoting the natural refrigerant. I think that's what I would like to say.
Hope everybody has got the copies of the presentation so far been done and circulated to you by Chandana sir. So if you have any doubts about those presentation slides which are shared to you, please do ask questions about it. It would be a good idea to have a more interactive sessions also, because the advantage of electronic media is that we are sitting in Pune and you are in different from parts of Lanka, but we are able to interact. But disadvantage is that we are not able to interact as much as possible when you are doing in personal capacity. So if you have questions of whatever we have discussed so far, and then what we are discussing today, tomorrow, please keep on asking the questions. We will be more than happy to talk about it more, and try to answer questions, whatever we know about with you. I know it's very short time. Actually, we are doing it say only 10 hours. We're trying to do learn the complete refrigeration of ammonia in 10 hours. But our objective is mainly to share what we know and try to use some glimpses of the ammonia refrigeration system. Maybe when this corona parts are vaccinations are completed in future, we may able to have a person to person discussion, more discussion, where we can be into more into interactive modes. But this is a
Yeah,
very interesting. This is a very interesting subject. As we are talking about, let me share something about myself. I am basically electronics engineer. I am not a refrigeration engineer. I am not a mechanical engineer. Whatever I have learned about ammonia refrigeration, I'm talking about it, I have learned through some books and mostly attending various technical sessions, presentations with senior members from the industry. That's how I learn it. But in my college days, I never learned about refrigeration other than the basic refrigeration cycle. And at that time also, I used to think why I have to learn this refrigeration. We had a one topic called heat power engineering. So I used to think about why I have to learn heat power engineering about boilers, furnaces, and this compressors and refrigeration. But then when I come into this field, I try to learn actually refrigeration, and I really loved it. I really enjoyed learning refrigeration. So it's ammonia refrigeration is something you keep on learning and adding every day. It's a very good thing. Very so many things happening into it, and every day it teaches you something. You can learn a lot about it. So, Chandana sir, do we have sufficient audience start today's presentation?
yeah, it is sufficient. Better to start
Okay,
now.
okay.
Yeah.
So, once again, good morning to you all and welcome to this UNEP, NOU and AR training program for the Train the Trainers workshop on good practices in handling ammonia refrigeration system. Actually, we are not handling ammonia refrigeration system. We are handling refrigeration plants to make the ammonia system working and try to find out what are the things are in the plant, how they work, and what we really want to happen into these plants. So our today's topic is effect of air and water in ammonia refrigeration plant. You may ask a question. Last 3 days, 4 days, we talked a lot of things in one day. Yesterday we had a different. Yesterday we discussed different components of system in depth. So why only these two items, air and water, for a full day seminar? So So let me tell you that air and water makes a lot of impact on ammonia refrigeration system. And your plant efficiency, your safety definitely depends on these two products. So when we talk about air and water, we know that uh, air and water is one of the most essential thing for a human being. Whether without air and water, the whole human being couldn't have been, or this life on this earth wouldn't have been there. We have to breathe the air, we have to drink water, and it's not only for the human being, but all the live things in on this earth, they work on the because of the air and water. But is this really good for when it comes to ammonia refrigeration plants? That's what we try to understand today. Whether as a human being, I inhale air, I drink water, and that keeps me fit and working. So, is it good for ammonia plant to inhale air or inhale water? That we try to understand today. Remember some of the slides which are shared with you every day. One is that how much electrical energy is required in from a plant in a refrigeration plant. Like I said, you talk about uh, ice cream plant, 70% of its electrical energy is consumed into refrigeration plant. When we are talking about dairy plants, 30 to 40% energy is consumed into refrigeration plant. When you are talking about frozen plants or freezing plants, maybe 70-80% energy goes into the refrigeration plant. So this energy, which is consume electrical energy, we all know it is high cost energy, or it is generated. It is meant by basically paying a very high cost to generate that energy. So we need to really need to see that whether when we are using this kind of energy, should I be consuming this energy inefficiently, or where it is not required. That's what the purpose of this total seminar is. How I can very conservatively use my high cost energy. Second important parameter is, of course, purity of ammonia. As it has been explained to you all the last 2 days, all refrigeration systems, whether it's with ammonia based or any synthetic gas based or any natural gas refrigerant, works on a pressure temperature characteristics of a refrigerant. And those pressure temperature characteristics are dependent on the purity of the refrigerant. In case of synthetic refrigerants, they are the depending on the mixtures of refrigerants which are used to create them, accuracy of that mixtures. Where in case of ammonia, it's the purity. We talk about 99.95% pure ammonia, which gives us the pressure temperature charts, which are considered to be the backbone of total refrigeration. So it means that when I want to achieve a minus 40 degrees centigrade temperature, my gauge pressure say minus 0.28 or minus 4 psi, then it clearly indicates that my ammonia will give me minus 40 if it is 99.95% pure. If my ammonia is not pure, what is means by not pure? Suppose this is 85%. It means it may have a water, it may have a oil or other non-basic gases like nitrogen, hydrogen, which will make my ammonia impure. And then I will not get minus 40 degrees centigrade at minus 0.28 bar pressure. Similarly, when about talking about condensing temperature of say 38 degrees centigrade, I must achieve so that time that 38 degrees centigrade to achieve condensing, my ammonia pressure should be 13.7 or 195 psi. Now, if find out my pressure is much higher, it means that my ammonia is not pure. It does not have the necessary contents, or it is unnecessary contents are there. And then instead of 13.7, my ammonia would be 15.4 bar pressure. It means that I am operating at higher discharge pressure, because of the impure of ammonia. See, these charts, I think we have been trying to show you every day. Main objective was to make sure that this purity of ammonia and the ammonia chart linkage is very important when we are talking about ammonia plant's performance, its energy efficiency, its safety of the plant operating. We talked about last 2 days about refrigeration systems. Well, mostly popular systems are gravity feed and liquid overfeed systems. And so these two systems where we have a receiver condenser, which a compressor, so which we call as a high pressure side. And we have the evaporators, accumulators on the low pressure side. So remember, this is a low pressure side system and this is a high pressure side system. When we have ammonia liquid overfeed system, it can be it will be we have a compressor, evaporator, condenser, and your high pressure receiver, oil separators, oil intermediate coolers that can be considered as the high pressure side. Whereas from low pressure side, we have a pump vessel, liquid recell filter vessel, what is called as a low pressure vessel, then ammonia pumps. Then we have different types of evaporators, arrangements of the automation, maybe hot gas defrosting, pressure regulation. This all, sorry, it is all part is called as a low pressure systems. Why this is important is that when you are talking about effects of water and air on ammonia plant, we need to find out where air will accumulate, where water will accumulate, and then we need to find out solution of it. So let's go now to see what happens is when there is a air into ammonia. We'll try to study both the things separately. So let's try to look at what happens when there is a air into ammonia plant. See, in refrigeration systems, or you all know fundamentally, basically pressure is additive one. It means that if you have different things into the refrigerant and ammonia, and there is air, or it is also called as a non-condensable equipment, non-condensable gases or foul gases. Normally, non-condensable gases, foul gases consist of, which are also termed as the foul gases, consist of nitrogen, hydrogen, some of the components from the oil, or because we are using mainly this synthetic oil or natural oil, they definitely have certain paraffins and other items. So, and of course, air contributes the major part of it. So the actual pressure is the pressure of a refrigerant plus pressure of a non-condensable. Typically, we call it air because air contributes maximum part of this non-condensable gases. But remember now, when we have a refrigerant pressure and plus there is a pressure of air, this is our total effective pressure is a addition of the both the pressures. That's pressure of air, pressure of nitrogen, hydrogen, and the ammonia pressure. So this total system pressure is combination of multiple pressures which are generated due to the refrigerant, air, or non-condensable gases. Now, how do we know we have a non-condensable gases in our system? Because, or we have a, so today we'll, instead of saying non-condensable gases, we will restrict ourselves to calling it as a only air, because air is a major contributor. But remember, when I mean air, it is a totally non-condensable gases, or also called as a foul gases. So what happens is that normally air and ammonia, when they come in together, as we say, pressure is additive. The total pressure of the system is pressure of refrigerant and pressure of the air. So when a gas enters from compressor to the condenser, you can find here there is ammonia and there is air. So when this thing starts from condenser top, the gas enters into condenser from a top side, and slowly it starts condensing and becoming a liquid. So when it becomes a liquid, the air does not get condensed because air does not condenses into that operating pressure range. So what we have here is a combination of liquid and non-condensable or gases. So how do I know whether my plant has a non-condensable gases or my pressure? So it is one way of calculating is that I can measure the temperature of the refrigerant into the receiver, and then I can convert its equivalent saturated pressure, and then I can measure the actual pressure. So pressure difference between actual pressure and the equivalent corresponding pressure of the saturated pressure of the liquid pressure is a non-condensable gas that quantifies the non-condensable gases into our plant. So what this non-condensable gases does to my plant? What does actually this ammonia do or this air does to my plant? So definitely, as I said, when we call about these gases are non-condensable one, it means that these gases does not evaporate or condense during my refrigeration cycle. Typically, our refrigeration plants are operating from minus 40 degrees centigrade, minus 45 degrees centigrade evaporation side to plus 38 or plus 40 degree on the condensing side. So during this complete temperature range or the operating range, air or other non-condensable gases does not get condensed or they does not evaporate. So they do not give any heat transfer to the refrigeration system required. Remember, our requirement of refrigeration plant is to have a heat transfer. That is the main reason of having a refrigeration plant. And now when this non-condensable gases remains present into the system and keep on getting uh, accumulating, what they do is that they do not operate the plants, but they keep on just running with the ammonia gas, and then yet they increases the electrical power demand because my discharge pressure is now increased, which is an addition of the refrigerant pressure plus non-condensable gases. As my discharge pressure increases, my compressor has to do more work, and this accumulation of air reduces my refrigeration capacity. So increases my power demand, decreases my refrigeration capacity. So overall, it decreases my plant's the system efficiency. Another thing happens is that because air is just circulating with the system, not producing any refrigeration effects, and increasing the pressure, which leads to the increasing the discharge pressure of the compressor or head pressure of the compressor. Now, as the head pressure increases, it creates problems on the bearings, drive motors, belt drives, gaskets. These failures of this components part in more failures occurs of these plants and increases maintenance cost and of course my downtime of the system. Now, due to high pressure, increase into the higher pressure, which is increase in the temperature, which also leads to breakages of component walls or the wall reeds, and also a possibility of breakdown of lubricating oil increases. So once my lubricating oil, which is being used into refrigeration system, breaks down, it gets converted into different components, and these components becomes non-condensables into the refrigeration plant. Now, due to increase in the temperature, the condenser scalings increases, and it also increases affects the performance of the condenser life, condenser performance, which increases the maintenance and of condenser and reduces the life of condenser. It is also said that due to increases into the temperature leads to the ammonia explosions, particularly when you are using piston compressors, possibility of ammonia explosions is high, and it may ammonia, which is now basically, you know, it's called as NH3, that is nitrogen 1 and hydrogen 3. How that ammonia is formed. It's possible that due to increase into this temperatures, the breakdown of ammonia are possible into two parts, and at higher temperatures it is more prone to get irreversibly breakdown into nitrogen and hydrogen. And this happens particularly with reciprocating compressor because they are operating at higher temperature. And now once this non-condensable gases, even this breaking happens of nitrogen, hydrogen, they remain in system and they are the non-condensable gases in this complete operation. What happens is when there is air into, see if you look at this shell and tube condenser, you can find that air gets accumulated on the outer surface of the coil. Whether it is or on the in shell and tube, it will get accumulated on the surface of the tubes. So naturally the refrigerant is here, and here you have air accumulated onto the tube. So heat transfer, air works as an insulation between the heat transfer. Same thing happens in evaporative condensers. You have this air getting accumulated on the inner surface of the coil. So it works as an insulator or a resistive element for a heat transfer. And then you have this performance failures. You can see here the air gets, this is the same, these two are actually similar pictures showing the different constructions of the tube. This is the electrical ones, and these are the round tubes. Air gets accumulated in the outer side of the tube, or in the outer in the inner side of the tube when it is a shell and tube, and on the outer side. So this accumulation of air reduces the efficiency of the condensers. So what actually happens? This is a typically for a minus 15 degrees centigrade evaporating and 38 degree condensing plant. If I have air of 0.5% in my plant, my pressure may increase by 1 psi and my power requirement will increase by 0.8%. But if I go to 4% of air, only 4% of air, my pressure will increase by 7 psi and power will go up by 6.5. Now let's talk about ammonia refrigeration plant with around 1000 kilowatt of power. So if you are increasing it by 6.5% of that, you are talking about 65 kilowatts of power per hour consuming. Just calculate how much money you will be paying because of the air. Now, how air enters into my plant? Okay, so let's assume that we agreed that air is not good for ammonia refrigeration plant. It is entering, having an air in plant is really not useful. So how the air enters into my plant? I think I missed some of the slides here, but let me talk about how air enters into my ammonia plant. Maybe some. See, there are ways by which the air enters into my plant. One is that when my plant is being pressure tested, there is possibility that it is all the proper vacuum is not being done. When that proper vacuuming is not done, so the whatever the air which is entered into the system remains the same, remains into the plant. Another thing is that when I am opening the compressors, I am opening any parts, like I am removing a filter, strainer filter for cleaning purpose or replacing purpose. When the filter is removed, that particular area is filled with the air. So most of the time operators, it is not possible for operator to vacuum that part and remove the air. If my compressor is open for servicing, the moment I open the compressor and remove those parts, air goes into the air gets filled into that plant. When I put the compressor back, that whole air does not get removed. That air get accumulated into the plant. Third part is that when my plant is particularly running at a low temperatures and say below minus 30 degrees centigrade, that plant is running in a vacuum, then any leakages through stain, leakages through the wall bodies or plant joints will not push my uh, ammonia out, but because my internal refrigeration plant is in vacuum, the air will enter into the system and this air will get accumulated into the system. This is one of the most way in which my air keeps on coming into the plant and air gets added into the system. So there is a possibility of air entering into the system through wall glands or any other leakages, particularly in the low side. Possibility of air entering into the system when it is some parts are open for maintenance and they are kept there when they are reassembled. The possibility of air when systems are being pressure tested, the proper vacuum is not being done. Some part of the air or the nitrogen which is used for testing remains into the system. And then there is also possibility of when my plant is in running condition, sometimes there is a possibility of air entering into the plant because leakages into the refrigeration systems. So now let me give you one example. When you intake air and it remains in system, it starts increasing your pressures. And as told you, when the pressure increases, possibility of nitrogen and ammonia breaking into nitrogen and hydrogen is also there, which also makes both the gases are non-condensable gases during our refrigeration plant and definitely affects the performance or makes the addition to the air. And then there is a due to higher, so once our we have a air in plant, our discharge pressures and temperatures are higher, possibility of oil breakage is there, which also leads to addition of these non-condensable gases. So these are the various ways in which those air enters into the plant, and normally air remains into the plant unless and until it is purged out. So air purging becomes very mandatory or important thing when we are running ammonia refrigeration plant. So air purging can be done in automatic way or the manual way. And when we are talking about manual way, it means by the purging walls provided in the manual systems, or automatic way, it means that there is a purging system installed into the plant. So let's say there can be three ways of removing this purging. A manual one is a direct venting of refrigerant mixture. Then there is automatic purging, or in which certain parts of a refrigeration is mixed with a compression. We are using an external compressor and being condensed and air and ammonia refrigerant is separated out. Another way is condensing the this refrigerant foul gas, as we call it, by using a heat exchanger and a refrigeration plant refrigerant capacity itself and separate out the non-condensable or air and the refrigerant. Let's talk about direct venting or manual purging. Normally, direct venting or manual purging is done at a receiver and inlet of the condenser. Typically, you will have a purge wall which is separate from the other walls installed on the receiver, and then it can be put it into a bucket of water, and this wall is when plant is shut down and totally closed down, this wall will be open, and slowly the wall will be open very slowly, and whatever the accumulation of air is there is drained into that water. Please remember, it has to be drained into the water only. You cannot open it to the atmosphere. It may lead to the leakage, ammonia leakage. Same thing can happen in condenser. You can have a purge wall at the inlet of the condenser, and when plant is you close down the refrigeration plant, keep the condenser fan and water running so that any ammonia accumulated into the this condenser is being converted into liquid and goes down, and then very slowly open the purge valve. Now, typical procedure, it is shown on the screen that a correct way of doing a manual purging, you have to use a PPE kit like mask, gloves, ammonia suit, then valve have to connect those, have to have a separate valves for purging at the top of condenser and receiver, connect a hose pipe through this wall to and then that keep that another end of that hose pipe with a connect some dead wet to that and then dip into the big water bucket. Make sure that water bucket is full of water. Then you pump down the refrigeration plant, make the refrigeration plant shut off by shutting the liquid wall at the outlet of the receiver. Stop the refrigeration plant, keep condenser fans running for an hour, and then slowly open the purge valve. Always monitor the watercolor foam formation in the water and smell of water coming from to the coming into the water. The moment there is ammonia, you smell ammonia, you find ammonia coming out of that purge point, immediately close the valve. Now, this is a very popular system, particularly into smaller ice plants or smaller plants with a single compressor or a two compressors, because it doesn't require any additional equipments or it does not require any supporting controls and automation. But this is also a very risky process. Remember, you are getting directly exposed to the ammonia. Possibility of ammonia leaking to the environment is there, and sometimes running away from this place is also very difficult. So make sure that you take all the precautions when you are doing a manual purging. So what are the another disadvantage? One is that you need to have take a lot of time because you need to shut down the system. You have to make sure that plant is totally shut down. Your condenser is totally liquidated. All the gas in ammonia in the condenser is totally liquefied, and then remove. There is possibility that total air is not removed. Refrigerant may leak into the system and the nearby people. In some of the places, it become illegal to release the refrigerant into the atmosphere or nearby people. And hence, normally, operators do not want to do it every day. They try to do it once in a month or maybe twice in a month. So what it actually means that when we are saying we are doing purging every month, it means that for 1 month we are allowing that air to be accumulated into the system, and then we are removing that air once in a. It is like cleaning a house once in a month. We are accumulating all the dirt and dust into the house, and then we are making sure that once in a month everything is clean. But it also means that for rest of the 30 days, my house is filled with the dirt and dust, and any negligence or any mistakes into this kind of purging will lead to the accidents, and it will lead to the air ammonia leaking to the atmosphere. So what's the alternative? Alternative is to go for a automatic purging. When I say automatic purging, it means it's a purging system which removes the air or non-condensable gases from an efficient plant without any human being or any human interference required. And secondly, it's an online purging. Online means it's keep on removing the air continuously so that there is no accumulation of the air into the plant. So what advantages I get if I go for a automated purging system? One is that increases safety of my plant because there is no staff or operators required to open and close the system. It makes sure that when my plant is open for a purging, no air or no outside equipments enter into the parameter items enter into my refrigeration system, and it is effective because it continuously operates, and multi-point purging can make sure that total plant is totally free of non-condensable gases or the air. It does not require a shutdown of the plant. It does not require labor required and the use of the personal protective equipment and climbing onto the condenser. Everything gets avoided. What are the disadvantages? There is always an initially higher cost of the purging system. The installation of purger, a proper installation is required. Then the pipings and the walls required for that. And secondly, is some maintenance may be required, such as the sensors or the solenoids are required into the plant. May need to change the solenoid coil or service those transducers. But overall, if you consider automatic purging, it definitely has more advantages than the disadvantages. So let's talk about the two different types of purging systems which are now in popular. One is called the compression of a mixture. So what has been done is that a separate condensing unit is provided, which takes the power portion of gas from receiver into the different compressor. It gets uh, compressed and then went into and put it into the, then that gas is being considered, put it into the heat exchanger where you have a subcooled refrigerant, and then if the non-condensable gases which are coming from this receiver are ammonia, they get condensed because of the low temperature. They are put it back into the system. If they are non-condensables, they accumulate on the top side of that heat exchanger, and then those are vented outside. So this advantage of this system is that it works irrespective of existing system. So whenever your plant is shut down also, then also the system will keep on running irrespective of your uh, refrigeration plant running. Disadvantage is that it requires a separate refrigerant, it requires a separate compressor. So your component required for maintenance are more, and then you need a separate electricity to run that compressor. A typical unit like this, you can see another disadvantage is that this has to be installed above your receiver or above the condenser. This cannot be installed anywhere into the plant. You can see this is a typical compressor mix, a purger with a compressor installed above condenser. The pipings are connected it such that it is connected to the receiver, and then you can see here some water bubbler over here in which the air is being drained. So if we have a multiple receivers, it becomes or condensers in a plant, it becomes difficult to connect one purger common to the system. But you may have to use different multiple purgers for multiple condensers and evaporators. Remember, in this kind of system, the drainage of refrigerant is very critical, and you have to make sure that you have properly drain it back to the system. Second system is using a refrigeration system itself, a refrigerant from the refrigeration system itself. What has been done here, that there is a small condensing unit here, or small heat exchanger is used, and then from a condenser or your receiver, the purge points are taken, and that foul gas is brought in contact with this heat exchanger. This heat exchanger is fed with a low temperature liquid from the plant. So heat exchanger is kept at low temperature, and when this gas comes in, foul gas comes in contact with this heat exchanger, if it is ammonia, it becomes liquid and it is drained back into the system. If it is non-condensable gases, it will accumulate into the this heat exchanger, and then it can be vented out. This venting out process can be done automatically. This is one of the most popular automatic purging systems which are being used. In earlier manual purgers with this same function was also used. They were providing multiple manual valves at the purge points, at the vent points, and then you can open this vent wall and open those purge valves manually so as to make sure that refrigeration is air is vented. But now more complex and more easy to use purging systems are available. You can see here a purger where you have a purge vessel over here and these multi points coming from condensers, receivers, a water bubbler. So when ammonia is when there is a venting of air is there, it is released into the water side, and only so that if there is some ammonia, this water ammonia will get dissolved into the water and only air gets vented out. What is being done here is that it's a fully automatic purging system. So you do not need an operator to run it or operate it. It keeps on monitoring the foul gases in system and it keeps on removing them. So naturally your condensing temperature remains very low. Also, in this kind of systems, normally you can see a wall connected over here and another here. So liquid which is fed into this heat exchanger, it comes through this and goes back to your compressor. And the foul gases which comes from here into the purge, what we call as a purge unit. If there is ammonia into it, you will find that there will be when ammonia is accumulated into this purge vessel, it is recirculated or put back into the system, so that there is no need of draining ammonia back to the system. It is used as a liquid for refrigerant for cooling the purge vessel and put it back into the system by using suction side. It does not require any external refrigeration system, so there is no power requirement. And what is the disadvantage of this system? Disadvantage of this system is that if a refrigeration plant is not working, is shut off, then this will not purge the air. But many times a owner thinks of, if I'm not running the plant, why do I need to purge the air? I need to purge the air only when my plant is running. Another advantage of this kind of systems is that this can be installed on the ground level. You don't have to install above condenser or above your other equipments. So it's easy to access and maintain. So what happens is when I'm having this automatic purging, see if it is a manual purging, if you look, consider this is as a pressure. If you, and this is the operating time. See, this is maybe your design operating pressure condition. So what happens is here, when there is air starts accumulating into my plant and there is no purging, my pressure goes high. I do a manual purging and then my pressure goes down. Then I get it to my desired condition. Then I stop purging. Then I again air starts accumulating into the time till the takes time I do the manual purging. If I'm not doing a complete and manual purging, removing complete air, there may be always some air accumulated into my system. If you see, this area shows the actual excess pressure due to the air, and this is my actual operating pressure. So this addition of pressure directly increases my energy consumption or the power consumption and reduces my efficiency of a refrigeration plant. You can see here is the actual place where a purger, before installing the purger, there was a discharge pressure of around 16.5 kg. And after purger is installed, system was running around 12 kg. This with the two-stage multiple compressors in this particular plant, there was 16 kg was earlier pressure, then it's gone down to 15 kg. The power requirement came down, if you see, from 106 kilowatt to 94 kilowatt, from 51 kilowatt has come down to 45 kilowatt. So total power requirement was at 139 kilowatt instead of 157 kilowatt. This particular plant was supposed to operate at -35 evaporating. So extra power of 18 kilowatt per hour was consumed, and at the cost of rupees 7.5 per kilowatt and 6,000 hours in a year, you're talking about 810,000 rupees per year. So if you consider the cost of saving happening just due to removing the air is this much. There is an additional saving in which is not calculated, which is the maintenance of compressor, reduction in the compressor maintenance. Because your system is operated at lower pressure, you are getting more energy efficiency. So you are able to achieve your temperatures faster and desired temperature achieved. So your product quality improves. If you consider all these parameters, this payback period of a purger becomes very low and system remains very, very crucial. Now it comes that well, purger is so good and so beautiful and it saves so much of energy. Why it is not popular or why there people complain that a purger does not work well? Actually, the performance of a purger is very much depends on the purge points or where I remove the air. I must understand where air gets accumulated into my plant, and then only I will able to remove that air. See to where to purge becomes very important. See, so naturally, I must say that if I want to purge the air, I have to purge from a place where air gets accumulated. So air will get accumulated on the high pressure side. It will never get accumulated on the low pressure side. Remember, it will not accumulate on low pressure side. Like on the evaporator side, possibility of air accumulation is very low. Air will always get accumulated in the high pressure side. Now, when I look at high pressure side, it means the discharge of a compressor, a condenser, and a receiver. So what happens is in a condenser, when my ammonia refrigerant enters into the condenser, the air and refrigerant both enter at the same velocity. So at the inlet of my condenser, air and refrigerant are at the same velocity, and at the end of the condenser, my refrigerant gets cooled down or becomes liquid. So velocity of refrigerant gas is almost zero at the end of the condenser, whereas the air remains at the same velocity. So if you consider the end of the condenser point where you will have maximum air and very less refrigerant or very less ammonia. So if I use this point to remove the air, then I will able to purge air more than the inlet. If I try to purge it from the inlet, then possibility of ammonia coming out is much more than the air. Similarly, when you talk about receivers, there is a receiver inlet point where you are receiving all the liquid and the air from condenser entering into the receiver. So at this point, if I have my purge point is very close to this point, possibility of ammonia coming from the point is more. Whereas if I go to the end of the receiver, my possibility of ammonia coming out is very less, whereas the air accumulation is very high. Another question is normally asked whether I should remove it from the receiver or a condenser. Now what happens is here is that air will remain in condenser when receiver liquid temperature is higher than the condenser liquid temperature. It means that if my receiver is at a warmer place, then it is open to the air. Somehow my receiver ambient temperature is higher. It will receiver may be a warmer than the things, or sometimes my cooling water is very low. It means my receiver condenser will be at condenser water is cooling down, and when there is a change in the refrigeration load, that is suddenly my refrigeration load is decreasing, it means I have a more condensing function occurring, then air will remain into the condenser. Another way, air will migrate more to the receiver when liquid temperature is higher than the receiver temperature. It means my condenser temperature is higher than the receiver temperature, then air will definitely move it to the receiver side. So when receiver is inside the cold room is nicely covered area, and you have some cooling water nearby to the receiver, it will keep the receiver cold. Sometimes due to change in the ambient conditions, the liquid temperature in my sump increases, which will result into the increasing the cooling water temperature of a condenser, and so there is a sudden increase into the refrigeration load. If my some cold storage doors are suddenly open, or I get a milk normally higher temperature milk in my pasteurizer, then my load is increasing. Then my condenser becomes warmer than the receiver, and then my gas will air will migrate to receiver. So these are the conditions. Some of these conditions are permanent, like location and warm location of receiver and condenser. But whereas the other conditions are not permanent, change in the load or change in the cooling water temperature is totally depends on other conditions. So you may have both the conditions happening in the plant at different times. So it is recommended that we have a purging points considered from the receiver as well as from the condenser. Third important thing is that should I make a one common condensing point from all the receivers and all the condensers, that will save on my purging points. But it may happen that these condensers or receivers sometimes are not balanced. Like pressure drop across equipments may not be some same, or there may be some installation errors. So it is recommended to have a multi-point purging system where we can take air or air from individual equipment and remove it. See, if you see, this is a typical evaporative condenser. As I told you, when ammonia is entering into it, air and ammonia both are at the same velocity. But by the end of the condenser, the ammonia is converted into liquid, and the air is remains as a gas. So liquid is at the bottom and air is at the top. So if you try to take a purging point at the inlet of the condenser, what will come out is only ammonia. Remember, we are not saying that air may be 5% or 10% of the total plant. So when we are opening this plant, when plant is running, maximum thing which come out will be ammonia, and your purger will doing the condensing work. But if I take a purge point from here, then only air will come out. Possibility of ammonia gas coming out here is very low, and then you get maximum air separated into the from the refrigeration plant. You can see here, this is a purge point which is provided for a manual purging, and this is a purge point provided for the automatic purging. And then you can have multiple purge. This here it is shown as a one for this condenser that has got two outlets, so it has shown one common purge point also here. Remember, this manual purging is to be used for a manual purging operation. This is to be used for automatic purging operation. When, as I told you about receivers, when liquid is entering into the receiver, do not have a purge point close to it. Possibility of ammonia is more. But if you go to the further end of the receiver, you will find more air coming out of it, because all the liquid or ammonia gets accumulated at the bottom, and what remains on the top is only the air. Vertical shell and tube are not very popular now, but once upon a time they were very useful. So when you are having liquid coming in, this point is where you have more of air, and liquid is drained at bottom. So you take this point at the outlet at the top of the condenser, because your liquid is getting at the bottom. These are some of the examples where some installation purge points are shown here. If you see, this is a PHE condenser. You have a hot gas or the air coming into the condenser and is going out. Now this is a nice U-trap plate here to avoid air or the gases going into the system. So you make sure that you are taking purge point before this U trap. So because we do not, this function of this U trap is to make sure that only liquid goes out here. So my purge point should be before this so that I can get maximum air from the system. Similarly, this is the evaporative condenser. You can see here a liquid lake going down and there's a U trap. So purge point is taken from here. This is a typical atmospheric condenser, and you can see from a common line, a purge point is being taken. This is another way. Normally, a purger, you can have a purge points. In this system, you can see if I have only put up a stop walls over here, and then purge points or the purge solenoid walls are installed at the air purger. Another option is that you have this solenoid walls installed at the outlet of the purgers, and then you electrically connect it to the system. Disadvantage of this system is that you have to run electrical cables up to this from this line to the purger. If you have the purge points at the purger, then only the piping is required. For multiple condensers, you can see here multiple purge points are being taken. Now, this is a little bit a tricky system. They have taken purge point from the immediately at the outlet, but then they have provided a U trap. So now this U trap is totally a big mistake, because what it means that you are trying to trap gas over here and allow liquid trap is being generated. So only liquid is being fed to the system. So that we don't want. What we want is only the foul gases to go to the system. So yes, you take a little bit up, but make sure this is one common pipe, not a U trap like this. This U trap must be avoided at the outlet for the purge points. It can be at the outlet of your condenser, but not for the purge points. This is a typical installation drawing for a air purger with a liquid overfeed system. You can have a multiple evaporative condensers. Outlets can be connected to the purger. A purge point can be taken from the receiver, and then liquid is fed from the outlet, low temperature outlet of the LP vessel or your pump feed line, and it's again taken it back to the LP vessel. So this, what I was talking about, this liquid line, make sure that this air purger or the purge vessel is cooled and condensed, and whatever the liquid is there, it is taken out. Now, when the foul gases comes from the outlet of this condenser, it comes in the contact with this coil, which is at low temperature. So it is ammonia, it will become condenses and become liquid. If it is non-condensable or the air, it will get accumulated into the refrigeration system in the purge vessel. If it is ammonia, you can see here a level switch is provided. So this level switch, if there is excess, there is a lot of ammonia getting accumulated, means there is no air coming out of the system. This liquid level controller will cut off the feed solenoid valve and then put this recirculation solenoid valve. So whatever the ammonia liquid accumulated into it, it will be fed back into the system through this coil. Whereas if this is non-condensable gases, then this can be electronic temperature pressure sensors, which senses the difference between the temperature and pressure of the ammonia liquid and the foul gases, and then vent it into the your air bubbler or into your water bucket. So this is typically for the liquid overfeed system. We can install a purger in gravity feed system like ice plant or a cold storage, as can be very easily done. Now here the liquid is fed from a high pressure receiver to the coil and is taken back. Now we can take it back to provide a separate slop pot, or we can put it back into the accumulator of your ice plant or a cold storage, and so that liquid separation takes place clearly. Only gas goes to the compressor, and a purge point can be taken from outlet of a condenser or at the outlet of a receiver. So, of course, the purger systems can be used into gravity feed system or into the pump circulation system. Does not make any difference. Only thing we need to take care of the this installation, proper installation, and you have to make sure you have correct system installed and purge points are taken correctly, then your purger will work and it will save you a lot of energy. So what happens actually when I'm having these are actually cost increased power cost calculation, which are on-site readings being taken and been monitored. Typically, it is made with the freezing plant at -40 and potato cold storage, which is running typically at -5 or -10 degrees centigrade for a 500 kilowatt refrigeration capacity. For a freezing plant, power required is 281 kilowatt. Potato cold storage is 148 kilowatt, and actual pressure is around 1.5 kg higher than the design pressure. The excess power was 19 kilowatts, whereas in potato cold storage it was 17 kilowatts. Now, freezing plants normally run longer time than the actual potato cold storage. Potato cold storage is lesser time. So I've considered your 5,000 hours. So typical increase in power will be only into the discharge pressure is this much, and this is for the potato cold storage. This also add the additional cost of running increase in compressor running hours because of the higher the discharge pressure. There is a damage. There is a maintenance cost of the compressor. So if you add all these things, it results into a huge potential saving and better performance of the plant. So this is we talked about all about air and its effects on ammonia. So as I said, it's air is not good for ammonia, is that we try to show here. Now we will talk about water. What happens is if there is a water into the ammonia plant. Now there is something that air does not mix with the ammonia, but it remains with the ammonia and it continuously flows with the ammonia. So you can say an air is like a person who is traveling in our railway or train without air, without a ticket. So he's taking advantage of traveling with railway, but he's not paying for it. Same thing is ammonia. It is traveling with the system, but it's not adding any effects of evaporation or condenser. Whereas in water, the case is totally different. Water actually, the biggest property of ammonia is that it is a soluble in the water. So ammonia, and we can say that ammonia has a very close affinity to water, and solubility of ammonia to the water is very, very high. So what we means is that if there is a atmospheric pressure of say 30 degrees centigrade, at a temperature of 30 atmospheric pressure and a temperature of 30 degrees centigrade, ammonia 30% of ammonia can mix into the water. If my temperature is at 0 degree, possibility of water mixing into ammonia is 46%. And when I'm at minus 30 degrees centigrade, 100% water will mix into ammonia. It means if at my ambient condition of 30 degree, the possibility of ammonia, 30% ammonia in water is there. At minus 33 degree, 100% ammonia mixing into the water is there. So you can see that you remember the first slide which I show you about purity of ammonia required. We need 99.95% pure ammonia to get the desired temperatures. Now what happens is when my ammonia or there is a water in ammonia. So when I'm talking about say at the pressure of minus 0.3 kg gauge pressure, 0% dilution, that is 99.95% pure ammonia, I will get minus 40 degree evaporating. If my ammonia pressure is say, 0 degree, I will get it minus 33. If I'm at plus 2 degree, plus 2 kg, my pressure, I'm getting about minus 9 degree. Now think of adding 10% water into this ammonia. So when I added 10% water to this system, instead of getting minus 40, I may be operating at minus 38.5. Or at 0 degree, 0 kg, I may instead of minus 33, I'm operating at minus 31.5. And at 2 kg, I'm operating at minus 7 instead of minus 9. Similarly, if I have a 30% of ammonia in my plant, which I say can happen at atmospheric pressure and 30 degrees centigrade temperature. At minus 0.3 pressure, my temperature would be only minus 32. So my plant at 0, it is minus 24 instead of minus 33. And at 2, it is plus 2 at minus 9 instead of minus 9. So what this tells me? What this tells me that if there is a water in my ammonia, then I will not get desired temperature at my rated suction pressure. It means if I'm running a freezing plant which is supposed to run at minus 0.3 kg to get minus 40 degrees centigrade, and then I have a 30% water, then I will be running only at minus 32 degree evaporating temperature. So my freezer will not operate at minus 30, minus 40, but it will be a gas will be only at minus 32. So it means if I have to get minus 40, I have to reduce my suction pressure. So much lower than minus 0.3 to place minus 40, or I will not get my desired temperature and my desired effect of a freezing of a plant. If I'm running a potato cold storage or a chiller plant to generate say plus 0 degree room temperature at my 2 kg pressure and minus 9 evaporating, I'm getting 0 degree room temperature. Now I'll be running at plus 2.3 evaporating. So it means my room temperature would be 9 to 10 degrees centigrade. So I will not achieve the desired temperature. So what this actually implicates is that when there is a water in ammonia, I will not get my desired suction temperature. It means that I will not able to run my plant at a desired condition. So how this water will come into my plant? There are two ways by which water can come into my plant. One is that during the time of the construction, during the time of the initial starting phases. Another is that when my plant is running. Of course, these are the only conditions. So what happens is when I'm running, when my plant is during construction or into the initial startup. So many times people do the hydraulic testing of a pressure vessel, which is not actually recommended. As AAR, we recommend to do the pressure testing using a dry nitrogen. We do not recommend hydro testing, but still many people do the hydro testing of a plant. And what happens is here is that when the plants are being hydro tested, possibility of water remaining into the plant is very high. The total water may not be get removed, and it will remain into the plant. Another thing which happens when these plants are under construction is that these water there are many pipes and joints. Pipes are kept open into the atmosphere. Sometimes partial work is done and end caps are not provided at the end of the day to the pipe, and this pipe will remain open. In the late night, dew will get formed onto these pipes, open pipes lying into the system, or the pipes which are not properly encapped. And then this next day morning, when people start welding or using these pipes, they will not take care of removing those dews formed onto the pipe, and this dew will get converted into water and it will remain into the plant. This condensation or dew formation is what I've been told. Then as the possibility of air, many times people use air for pressure testing of the plant, instead of dry nitrogen, they use the same refrigerant compressor to put the air into the testing. Now this air which is sucked from the atmosphere, it has got inbuilt moisture in it, what we called as the relative humidity of air. That moisture will go into the refrigeration plant, and it will remain into the plant. It will not because it will be impossible to do the complete evacuation of such water. Third thing is that there is a possibility of ammonia which is supplied to you is not an anhydrous ammonia. It is a hydrous ammonia may be supplied to you because many ammonia vendors do not provide purity certificate of the ammonia which is being supplied. Sometimes it is bought it from the, instead of bringing it from the cylinders, whole capsule is bought from an ammonia plant manufacturer, and then we do not know what is the content of the water content into the system. Another way is that when you are charging those ammonia cylinders into the plant, if you remember, many times the pressure inside the cylinder is higher than the pressure in the system. So the ammonia starts, when it is connected, cylinders are connected to the system, ammonia goes from a high pressure to low pressure. Then operator wants to make sure that all content of ammonia from the cylinder is being done. So what he does is it tilts the ammonia cylinder by 180 degrees. So normally water accumulates at the bottom of the ammonia cylinders or ammonia plant, and ammonia is in the top of it. So when you tilt the ammonia cylinders by 180 degree, all the water which is in the cylinder makes it is 100% guaranteed and made sure that is poured into the refrigeration plant. So our water will remain in the system. These are different ways. When initial stage of you get the water into the system which remains there. Another is that possibility of rupture of heat exchanger tubes, which are particularly like shell and tube chillers or ice bank tanks or coils in your ice plant, where that other side is a liquid or a brine, and then when there is a damage or leakage into that tube, the other side refrigerant will leak into the water side or the brine side, and the water will enter into the system. And when your plant is being running, it is possible that proper procedures are not followed when draining the oil or refrigerant from a vessel or charging the oil, and possibility of water into the system is also very high. Systems which are basically operating below atmospheric pressure, there is also possibility in the vacuum gauge. In case of leakage in valve stems and hoses, the air will enter, and along with the air is a possibility of water moisture from the air entering into the system. So what happens is that this any improper evacuations or the services were done into the maintenance work leads to water entering into the system. Sometimes there may be some chemical reactions which happens between ammonia, water, oil, and it may generate water from this oil or other components. One more is the failure of purging, or there is no purging. We will see more about it. What happens if there is no purging? If let's assume that we have a purger plant, a refrigeration plant with a purger, which is removing 5 liters of air per minute from a refrigeration plant, and ambient temperature is typically a coastal condition of 35 degrees centigrade with 75% RH. It means 75% RH at 35 degrees centigrade also means there is a 25 grams of water per kg of air. Now, if we are removing 5 liters of air per minute from refrigeration plant, it means that air of 5 liter is somewhere entering into the refrigeration plant. So if considering 75% RA, it also means that there is around 7.6 grams of water entering into the refrigeration plant, which is not being removed. Air purger will remove the air, it will not remove the water. Why? Many people say that purger removes the air and water. A purger will not remove the water mainly because water accumulates on the low pressure side, whereas the air accumulates on the high pressure side. If you have seen, we have seen the purging points are taken from the condenser receiver, which are the high pressure side, where possibility of water accumulating is very, very less. So by this way, simply because your purger is working or your air is entering, you have around 500 liters of water accumulated into plant in a 10 years plant. This is one of the source of getting water into the system. So what happens is when there is a water in my system, what's wrong? I drink water every day. My human body needs water, but it does not mean good for the refrigeration plant. What will happen is that the moment we have a water entering into the plant, running in it, and if we have a air, then corrosion will start because most of the ammonia plants are made with the steel equipments. When the water come in contact with oxygen, the steel corrosion will start. When the water comes in contact with the oil, mixes with the oil will deteriorate at a faster rate. Oil quality will fall down, viscosity will go up, and oil failure is very high. Your replacement of oil required will be much higher than the regular one. Also, when the oil is starts forming organic acids, because those are the natural oils, they may generate have some organic acids, and then that will create a sludge formation, and then that will start damaging the compressors. There will be, because of the failure in the compressor, there will be oil failures that will lead to the more wear tear of the compressor. You will need more oil changes, more oil filters are required to be replaced, which will increase the plant running cost, increases the service cost, and also increases the shutdown cost or the plant shut-off cost for a maintenance purpose, which means you need to have extra plant capacities or you will suffer into the production. Now, as there is a water into the ammonia, there will be pressure drops increases through the pipe because the sludges and corrosion and sludges will reduce the effective area of the pipe, and then that will reduce into the increasing the velocity of the refrigerant and increasing the pressure drop. Then mostly when you are using ammonia pump systems, possibility of failure in pressure, adverse effect of ammonia pumps will be there, because ammonia pumps, they are very special pumps. They are not your typical, they are not meant for a water pump application. So possibility of this pump failure becomes very high. And then you will be operating at lower suction pressure than the design one to maintain desired temperature. I have explained this to you on the slide, how much it will be going down. You will be operating for a minus 0.3 bar. If you have a 30% of water, you will be operating at minus 32 instead of minus 40. To achieve that minus 40 or minus 8 degree difference, you need to learn at much lower suction pressure. So I will be operating at lower and lower suction pressure. I will not get my desired temperature. It clearly means my system efficiency will drop down. It will be increase in power consumption, the reduction in the overall quality of my plant will efficiency will go down, my product quality will go down, electricity cost will increase, there will be more choking of the filters, damaging to the equipments, and this all will lead to the continuous failures and continuous shutdown of this. You can see here the actual photographs, how the bearings are damaged due to the water. These are the photographs taken from a screw compressor servicing engineered by one of my friend. They shared these photos with me. You can see how this bearing get damaged, how the screw rotors are damaged over here because of the water, how the compressor body is contained, the sludges are formed into the compressor body, how this there are, you can see the markings over here, these markings which has actually resulted into the failure of the compressor. This one is from a piston compressor. You can see how it has affected how the water has affected, sludge has formed into the system, and how overall a compressor has failed, how my maintenance cost has gone up. These are the actual photographs where we monitor there is a heavy water content into the ammonia plant. And typically, you can see how the filters get sludged, clogged, like you can see over here. These are the, when this oil is, this look at the water content showing into the compressor side glass. And when it is drained, you can see how much is the water into this oil, changing the color of the oil, damages happening to the oil. It means my failure of my continuous replacement of the oil filters, continuous replacement of the oil, and increase in the maintenance cost. So what happens is here, this is shown as a typical graph. There is a bearing life and there is a percentage of water. So bearing life from say, normally if you're running at say 100% capacity and then you have a 0.2% water, and if water goes to 0.5%, your bearing life comes down very, very low. See typical rated oil, and this, if you look at this shows how much a bearing of my compressor will fail when there is a water into the system. These limits are shown here, that when there is a paraffinic mineral oils, you can have a maximum 100% of 100 ppm of water. For naphthaminic mineral oils can be 150 ppm. For synthetics, it can be around 1000 ppm. But if there is more percentage of oil, as I'm going from ppm to percentage, it means my bearing life will reduce tremendously, which will result in the failure of bearing, failure of compressors, higher maintenance cost, and higher operating cost. Now, where does this water will accumulate into my system? It is very simple to say that water accumulates on the low pressure side. It means it will accumulate into recirculator vessels or pump receivers or LP receivers. When it cases of the ammonia pump system, in flooded systems, it will be into the evaporators. In DX systems, it will be in suction accumulators. And when I have a two-stage systems, whether it's compound compressors or a two different compressors, it will be into the lower evaporators of the low side refrigeration systems. Let's see why it happens like that. Why water gets accumulated into the low temperature, low pressure side. The main reason is that there is a vapor pressure difference between water and ammonia. For example, you at 2 degrees centigrade, the vapor pressure of ammonia is 3.6 kg per centimeter square, whereas that is of the water is 0.007 kg per centimeter square. You just see how much is the huge difference between the vapor pressure of ammonia and water. So when you are running the plant at a 3.6 kg suction pressure, your all ammonia will get evaporated, but water will remain accumulated into the low pressure vessel. It means that the liquid with the higher vapor pressure evaporate faster. Because that is what we are running the pressure system. We are not going to the pressure of 0.007 kg. So water will not evaporate. It will keep accumulating into the ammonia refrigeration system. So typically when I am running at a temperature of 0 degree evaporating, the water pressure could be 0.6 and ammonia could be 3.29 kPa. Now, if I am having a temperature of 15 degrees centigrade, water could be at 1.71 kPa, and the ammonia could be 6.29 kPa. So you can see there is a huge pressure difference for different operating conditions for water and ammonia. This basically that pressure, vapor pressure difference keeps the water accumulated into low pressure side. So next question is that, can I measure the water content into ammonia plant? We have seen that we can measure or calculate the air content in a refrigeration plant by measuring the actual pressure of a receiver, and then measuring the liquid temperature in the receiver and converting it into saturated pressure. We can get the difference between the condensable, difference is condensable, non-condensable pressure. Similarly, can I measure water content? One simple observation is that you find out what is the suction pressure at which your compressor is running and what is the effective suction temperature you are getting. If there is operating at the similar condition, possibility of water is less. But if your desired suction pressure, design suction pressure, actual suction pressure and pressure and the temperature operated as the actual as the desired design pressure is not same, it is possible that there is a water in your system. Now here I will try to, but if there is a possibility that you can measure more moisture or water content into ammonia by using an ammonia sampler. So what I need to do is an ammonia sampler or a test tube. There are some holders for the test tube, and then the test tube should have a marking on it. And then I need to keep a holder to keep these things. And of course, I need to use PPE kit, my face shields, rubber gloves, so that I can be protected when doing. So what is the sampling locations where I can take? As I told you, the water is likely to accumulate in the low pressure side of the system. So I can take it from the pump systems. I can take it from the infrared systems. I can take it from the oil drain points which are provided into the evaporator sites or surge dumps. So, or I can take it from the suction accumulator in the DX systems. You can see here, this is how a typical ammonia sampler looks like. You have an isolation wall, there is a regulation wall, a non-return wall, a handle to hold the things, a vent tube, and there is a test tube which is marked with the percentage. This is a marking in millimeters, will tell you what is the content of the ammonia. So what is the procedure? Make sure that you wear all the protective clothing, that PPE kit, face shields, and head protection. Connect the sampler to the your outlet of the ammonia tank. Make sure that glass to be is securely attached to the covered outlet. It means that it is this is totally assembled unit. You connect this point to your sampling point, and this vent point is taken further away. Close the wall at the sampler converter, crack the wall at the tank. That is the tank where you are taking the ammonia sampler. First you close these walls, and then you just crack the wall which is connected to the from the drain point, and then you make sure there are no leakages. Then slowly open the wall, and then wait for the this air to pass through these things, and then you open this wall slowly, and this wall very partially, and there is possibility of air initially coming from the hose connected to it. So let that air get passed. You may have to wait to get the ammonia sampler, a known quantity of the sampler, maybe 5 to 10 minutes, 15 minutes. It's possible that initially the lot of oil or sludge will come into ammonia. You take a measured quantity into this sampler, say 100 ml sample over here. If there is lot of surge and there is lot of dirt coming into a, then you close this wall, you close this isolation wall, close the wall on your system drain point, check the color and the quality of the ammonia you have collected. If it contains more dirt or oil only, then remove this tube, replace with the fresh one, and connect the sample again. And then once you have collected the sample, wait for at least 5 to 10 minutes, and then you take this ammonia sampler out, put it onto a stand where this will be kept into the ambient temperature condition. And what will happen is that the ammonia inside this tube will boil and it will vent into the atmosphere, and what will be remaining will be the water. You can measure that water quantity, and then you can convert using a typical chart, percentage of water, and depending on the ml of residual to the percentage of the water. So can I remove my water automatically from my refrigeration plant? That's the important question comes in, because okay, I found out that there is a water in my plant. So what I can do with this water? How can I purify my ammonia? Typically, larger ammonia plants may contain 500 kg or maybe 1 ton, or even I have seen the plants with 10 ton of ammonia. So it is not practically possible to throw away all the ammonia and replace the one. So there is a procedure or system which is called as the ammonia purifier or ammonia dryer. What has been done in ammonia dryer is that liquid samples are taken from a low temperature site, maybe a pump vessel, or from ammonia on the oil drain pots on the your gravity fed systems, are fed into a vessel. A vessel contains an heat exchanger. Heat exchanger vessel is normally fed with the hot refrigerant from HP receiver, or maybe hot water, or maybe an electrical heater, depending on the system requirement. So what happens is here, the this ammonia sample, which is taken from a pump vessel or a evaporator drain points, come into contact with this hot refrigerant. Hot refrigerant will evaporate any ammonia content into this. That will go back to the system. And if there is any content of water or moisture will get accumulated at the bottom of this, then it can be drained. This is a level controller is used to make sure there's no excess ammonia getting over here. If there is excess ammonia, so there should not be a liquid stock coming into it. So this is how a liquid supply system will work. This shows a typical P&I diagram of having. See, this is your tap point for the low temperature from LP receiver, and then we have this hot liquid which is going from high pressure receiver to LP receiver, is routed through this heat exchanger and fed back to LP vessel, and this heat coming from this high pressure receiver will evaporate the ammonia, and the liquid will get accumulated at the bottom. So this is how this system will work, and it will purify the ammonia in the system online. The liquid can be drained directly. So this shows a comparison of a two-stage compressor system with a two-stage compressor or a booster compressor. Because I'm considering booster compressor over here only, because as I said, water gets accumulated onto the low temperature side, not onto the high side. Two-stage compressor means a compound compressor. So you can see that there is, if there is a water containing contamination, what is shown here, the refrigeration capacity considered 300 kilowatts. Now the booster is condensing at -7, whereas two-stage is condensing at +40. Both are running at -80. Since this is only a booster capacity, it is 80 kilowatts. And its two-stage total power required is 171. If now we have a 10% of water, so instead of minus 40 degree, we will be going down to minus 42. So from minus 40 to minus 42 degrees centigrade, it means that I will be requiring uh, more power, more power instead of running power. So instead of 80 kilowatts, I will be requiring 88 kilowatt. And from here, 171 kilowatt, I will be requiring to run at 182 kilowatt. So if you consider the 6,000 hour operation, because of the little bit of water, 10% of the water contamination, I will be spending a huge amount every year. So this is what the cost of the water in terms of only suction pressure. To achieve that suction time evaporating temperature, I have to operate at lower suction pressure. But now this is only one. But there is additional cost of the compressor maintenance, choking of the filters, filter replacement, oil frequent failure of oil, replacing the oil, and corrosion, sludge formations into the strainers. So that replacement, cleaning, shutdown of the plant, you need to add all those when you are considering the costing. So this is what actually totally talking about effect of air and water in ammonia refrigeration system. So what happens when there is air in system? It increases the discharge pressure, increases the power consumption, reduces the refrigerant capacity, increases the wear and tear, increases the scaling on the condenser, and overall it costs money. Secondly, when there is a water accumulation, water always accumulate on the low side of the vessel. And then, as I told you, ammonia, because of its affinity with water, there will be immediate mixing of water and ammonia when they come in contact. And from anhydrous ammonia, it will be hydrous ammonia, which will change operating condition. And then this presence of water will contaminate the water. Water contamination will be lower the system efficiency because we will be operating at lower suction pressure. Of course, when you are operating at lower pressure, suction pressure, it means you are operating at higher electricity cost. Then there is a corrosion of the refrigerant equipments. There is a corrosion in the piping, in the walls, in the evaporators, in the condensers. There is a earlier aging of the oil, damages to the oil. So replacement of the oil becomes more frequent. Then there will be damages to the compressor, bearings, filters, and then there will be a higher maintenance cost of the compressor and the compressor spare parts. So our shutdown times will be more, and this all will lead to a lot of loss of these systems and energy efficiency. So that's the end of the presentation. Give me a second. I would like to show one or two videos about this ammonia systems working, this particularly ammonia water draining, and some of the things I would like. Just give me a second to run those, try to run those videos on air purger operations. And also I would like to show a video of how this ammonia sampler work. Just give, let me run those videos for you. So you can see how the actually systems are working. Uh, is my screen visible, sir? Are you able to share see the video from my screen?
No,
No,
I
visible,
cannot.
not
Not
visible.
visible. Not visible.
Okay. Now I'll try again. Is it visible now?
Not yet.
Now?
Yeah, it's okay now.
Yeah, it's fine.
Just see. This is a draining of the water in a dairy plant. This liquid was drained from a dairy plant. Yes. Okay, I'll share the screen again. This is a video of actual ammonia sampler being connected into the system and how the ammonia has been collected. And a sample of the water quantity has been calculated. If you see, this is a pump vessel outlet where the wall is connected to take the sample into the sampler. You can see the ammonia collected over here. So after some time, this is the last video I'm trying to share is about uh, ammonia air purger operation. It's installed into Unilever plant. You can see how much the air is being purged into it.
So is it an automatic one? Huh?
Yeah, automatic one, sir.
Oh,
It was quite a big plant. We have installed two automatic purger systems. The plant was at -40 evaporating and almost 1,000 tons of refrigeration capacity. So initially there was a lot of air being removed from it. This is the control unit for that purger. So that's all from the today's presentation part, sir.
yes, sir, we got a lot of idea with your videos. Thanks.
Thanks.
Yeah, thank you very much, Mr. Joshi. And I think we got more details regarding the purging and the moisture. So thank you very much.
Thank you. Thank you very much, sir.
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 Thank you very much.
Thank you very much, sir.
Thank you very much.
Thank you very much, sir.
Thank you very much, sir. Thank you very much, sir.
Thank you, sir.
So if there are no questions, then we can stop today. Sanjay sir.
Thank you very much.
Anand sir, which kind of the desiccant we can use for the ammonia?
Ammonia, you don't need to use desiccant, sir.
Desiccant,
Not required. Not required.
Not required. Just only dehydrator.
Yes, dehydrator one in common system, and normally a filters in your liquid lines are more than sufficient.
Okay, thank you. Are there any questions?
Hello.
Yeah, can you speak? Yeah.
Sir, can you tell me what is the meaning of low charging ammonia system and how we differ the standard system?
I think that was Mr. Gulanikar informed you on the day one about when you're talking about refrigeration system. Basically, when you are building a larger scale of the ammonia refrigeration system, the quantity of ammonia per ton of refrigeration, normally when you have a bigger system is more. What has been thought of is because of the toxicity ammonia to have a smaller quantity of ammonia, lesser quantity. So you can say earlier it used to be around 6 kg or 7 kg per ton of refrigeration. Now it has brought down, it has come down to around 2.2 pounds per ton of refrigeration, or some plants have smaller one. I've seen ammonia water chiller of 300 TR water chiller built with around 35 kg of ammonia. So using lower charge of the less quantity of ammonia is called low charge system. There is no such definition in terms of how much is the low charge. Typically, around 1 kg per ton of refrigeration can be considered as a low charge system. When you are talking about chiller packages. However, when you go to the lower temperatures, because ammonia is used for different applications, the charge quantity may vary depending on the temperature also.
So can you reach the -60, -40 by using ammonia?
Ammonia has been used up to -50 degrees centigrade. You cannot use ammonia below -50 in a normal vapor compression refrigeration system.
Okay. Thank you, sir. Sir, I have a small request for you.
Yes, sir.
Sir, have you done any case study or research paper for the using ammonia plant, like energy saving concept? So have you done like that research or anything? Can you share the link for our instructors to refer that one?
We have done a lot of actual case studies of doing energy saving into it, and tomorrow we are going to have some case presentations into this case energy saving aspects. Tomorrow we have Gulanikar is going to make a presentation on his case studies. In the meantime, I will share you some articles with you, which Chandana sir he can share to all of you.
Yeah, I can. So.
Okay, sir. Thank you very much, sir.